Great. I love that enthusiasm. Okay. So,
before you start, could you turn off the lights?
yes. Perfect. Thank you. Capital suggestion. I might also trip, or try not to trip on my shoelace, because although that would be a very comical moment for the stream, I'm sure I would injure myself, and then that's just a hassle, So in our last lecture, we were going over digital design techniques. This slide here shows a nice little summary of the entire process. So the digital design process summed up, first, you will have some kind of problem description. This problem description may be given to you by a client, it may be given to you by another department within your company. At any point, it is a description of the problem which your circuit is meant to solve, or your controller. From this description, we then derive a truth table, or similarly rigorous description of the outputs in terms of the inputs, right? It will often happen, because real life is a thing. It will often happen that your problem description is insufficiently detailed to fill in the entirety of your truth table, right? So you basically have two options at that point. You either say, well, if they didn't cover that case in the problem's description, then I guess that case doesn't matter. This is generally translated to what we call a don't care value. That can be represented as like D, DC, or X in the table. Just generally things which the problem itself does not suggest one way or the other whether that should be a 1 or a 0. So, essentially, it doesn't matter either way. That's one way of interpreting it. The other way of interpreting it is, I guess my problem description is not sufficiently detailed for this application. Perhaps I should go and ask for clarification, either with the client or the department or whatever, or what have you. See if you can get the missing entries in the table filled out. Right? Generally speaking, probably a combination of both is the best approach. But you should always seek more information first. Because, seeking the information after you've made the design decision just means you have to redefine and redesign your design, which is costly and expensive and not, the most conducive to keeping your job. So, once we have a truth table or similarly rigorous specification, we can derive from that output equations. From those output equations, we can minimize the output equations, possibly using Karnaugh maps. And from this minimized description, we can derive our actual logic circuits. Does that make sense? That's the whole process, sort of big picture. So, I'd like to switch gears somewhat and talk to you now about sequential circuits. So up to this point, all of the circuits that we've been talking about have been... I guess that didn't work, eh? You know what? I'm just going to shout at you. Oh, there's the clip. Uh-oh. guys. I apologize. That was bound to happen eventually. Okay. Sorry. Give me 1 second here. So, everything up to this point has been combinational logic, right? There's been no concept of time, right, just yet. What I mean by that, everything that we have done in the previous, I'm still going to use it as a pointer though. Everything that we've done in the previous design process is essentially assumed to occur in one clock cycle, or to have taken place sufficiently quickly that you don't have to worry about the clock cycles, right? Once we start getting into sequential circuits, we start worrying about clock cycles. So what we mean by sequential circuit is we are starting to introduce the concept of state, right? State in the form of registers or shift registers or counters or, things which have flip-flops as their base circuit, right? So this changes the game completely. In general, and this kind of comes back, y'all remember our general purpose controller design from like the first couple of weeks in this course? You guys remember that? You remember how we had within our CPU, we had our control unit, we had our ALU, and off to the side we had a bank of registers. The control unit basically controls which operations take place in the ALU, and it controls the loading and unloading of registers from the ALU, the interaction of register data with the ALU, both loading and storing, right? So there's a reason that you keep the registers off to the side, right? You don't mix it into the ALU. When you start introducing state, things can get very complicated very quickly, right? So what we do as a sort of, the way that we design these sorts of things, we keep all of our state in one place, and we sort of have the combinational circuit on top of that, receiving inputs, and then interacting with the state elements. So, in general, what we're going to end up seeing here is we'll have inputs, which would be external inputs, right? These come into a combinational circuit, right? This combinational circuit yields its results to the state holding elements. State elements. These are generally called registers, but I'm going to use the general term state elements for now. These state elements then feed back into the combinational logic in order to be used in the process of updating the same state elements, right? This is the same concept as using a variable to determine the next state of the same variable. So without this feedback here, there would be no possibility of an increment operator, for instance, right? So from this, the question we then derive is, where do the outputs come from, right? In this diagram. there are two approaches, essentially. The first approach to this is called Moore architecture, no relation. In Moore architecture, the outputs are derived purely from the state elements, right? So this would be Moore output, no relation. The alternative style to this is called Mealy. That's Mealy output. So you have one or the other, not both, but I'm putting both on this diagram to show where they both come from. So in Mealy outputs, you are deriving things both from the state elements as well as from the results of combinational circuitry, right? So advantages, disadvantages. In the case of Moore output, this will generally have an effect of reducing the length of the critical path, right? Which is, So when we have these long series of digital circuits, right? These logic circuits, the speed with which that circuit can be updated with new values is limited by how long it takes the electrons to propagate through the circuit, right? It depends on the slew rate of the transistors and other associated electrical properties, right? You can get faster update rates with better transistors, but you can also get faster update rates by using fewer transistors in the critical path, which is like the longest path that needs to be updated, the one that's the bottleneck for your calculation, right? Moore architectures tend to reduce the size of the critical path, but they use more registers in general because every output has to be registered even if it doesn't necessarily need to be, right? Like if it didn't need to be in Mealy architecture, it would need to be under Moore. So you'll need more registers in general, but more registers don't increase the length of the critical path. Mealy requires more combinational circuitry in order to be able to draw from it to produce the output, but in general, you can have like less size occupied under Mealy. So Moore slightly faster, Mealy slightly smaller, Mealy generally preferred. Make sense? Any questions? Okay, good. So I'm assuming we all know reasonably well what a register is at this point, but we'll see what these slides have to say about them. So the design of these circuits which involve sequential components is generally in line with what we have seen before, but now we have the added complication of the additional inputs and outputs which are represented by the stored data, right? You can kind of conceptualize this, right? Whereas with pure combinational logic, you have your inputs, you have your outputs, that's all she wrote. When you have state elements in there, every wire data bus, all of the information traveling into the state elements can correctly be thought of as outputs of the combinational logic. Similarly, state element, like the existing values of state elements, can be thought of as additional inputs into the combinational logic. So every state element that you add is a kind of implicit input or output to the system from the perspective of the combinational logic. Make sense? So it makes it a little bit more complicated, but a lot more useful. So, so sequential components. Here we have illustrated number 1, A, your most basic set reset flip-flop. Right? So, you guys done these? You guys know how these work? I'm seeing nods. Anybody know? A couple of people? Okay. So, with a set reset flip-flop, the set line sets the output as being 1. The reset line, if that's activated, resets the, well, it resets it to 0, right? So, if you imagine, you know, an initial state on this of, you know, this guy being false, right? This guy here being false. If we set this guy to 1, right, then this is 1 and 0, right? ORed together is 1, knotted 0, right? This becomes 0, that becomes 0, that becomes 1, right? That 1 gets fed back, but it doesn't change the state here. Interesting little, thing about flip-flops. Think about the initial state of a circuit like this, right? Because it's dependent wholly on its output, but it's being fed back in, right? What's the initial state of a flip-flop? Right? It's actually random. Or not necessarily, like random from a design perspective, but it's dependent on the exact physics and the amount of time it takes electrons to pass through these 2 wires on your physical board. These things can, you know, you can have a flip-flop that turns out as like starting at 1 like 80% of the time, and 20% of the time it starts as 0. Like they're subject to those types of like instability upon powering up, which is why one of the things that you do as part of your power-up routine is you clear all your registers, because you can have junk data in there to begin with. So that's a set reset latch. It's a latch because it'll hold its state until such time as it receives either the set or the reset signal. If we add to that a clock signal, right? The clock basically gates the set and the reset signals so that this flip-flop does not get updated so long as the clock is low, right? Question?
When it says that 1, 1 is undefined, does that mean that it will output any of the other 3, so either do nothing, reset, or set it to 1?
Well, let's see. So, I guess it depends, maybe it depends on the previous state, let's see. So, we got a 1 and a 1, right? So both of these are 1, so both of the outputs are 0. Except, yeah, it seems like it would output 0 to me, but yeah, I didn't make these. I didn't make this slide, so I don't know what the point was of that. Generally speaking, you either set or reset flip-flop. You don't try to do both at once, because you know, yeah. Because what would the point be, right? But anyway, so. This little app, yeah?
It has to do with Q and Q bar.
Has to do with Q and Q bar.
The undefined, since they're both 0.
Okay.
Like, it's either like, you know, they have to be inverse of each other. So like if they're both 0, then they're basically the same thing.
Yeah.
Which is not supposed to be the case.
Yeah, okay. But they do have values.
Yeah, but they're supposed to be the opposite of each other.
Yeah.
Q and Q bar are supposed to be opposite, but they're not.
So it's an error state,
Yeah.
essentially.
It's not supposed to.
All right. So take this and interpret it as error state then. Yeah. Thank you. Yeah. There we go. So, anyway, so the clock signals are extremely important, right? Like, hopefully I don't need to go over that again, but yeah. So, we take all of that and we kind of collect it into a black box, right? For a regular, for the set reset latch, right? We kind of just collect all of those functions. We can ignore the actual circuitry. We can just deal with it as in terms of its inputs and outputs. So if you take your data line, right, or if you take a data line, you invert it, set it, put it into reset, and just allow it straight to come into set, what you have done is you have transformed a set reset latch into a D latch, which is to say it just takes one input, which is the data coming in. So whatever the data is coming in, that's what will be preserved, right? If this guy coming in is 1, it sets 1. If it's 0, it gets inverted to 1. That gets reset, which means that the value stored by the flip-flop is 0, right? So yeah, that's how that works. Yeah, I'm going to skip that one. So, to construct a register, we take an array of these data, of these D flip-flops, and attach them all to the same clock signal. And Bob's your uncle. That's all that a register is. It's just an array of these flip-flop components, right? Fairly straightforward, right? Good. Am I boring you guys? Have you guys done all this before? Okay. I'll try to zip through it then. So, counters then, right? Basically the same thing as a register, except you're taking the output from the low bit, right? Running it through an AND gate attached to the clock signal, so it's only going through when the clock's enabled, right? We are setting that into the next bit. So this, over time, has the effect of, this guy will be 1, and the rest will be 0. He'll be set to 0, the next guy will be 1, etc., etc. So a binary counter, right? So much for sequential circuits. How many of you guys have done finite state machines? Oh my goodness, practically all of you, actually.
It was in a course last semester.
Excellent, good. Okay, so we don't have to dwell on it too heavily then, right? Good. I know that a lot of this is review from last semester, but it's in the accreditation requirements that I have to cover it, so we're going to cover it. Got to get it in before the exam so I can put a question on the exam about it. At least one question. Ha! All right. Anyway, and that's your hint for this evening. So we have discussed, we've discussed both combinational and sequential circuits. Let us consider a system that is on the next page, and we'll analyze this system. Yes, thank you. Quit, thank you. So let's consider this system, right? We have some number of combinational circuits. We have some registers. Just looking at this, is this Moore or Mealy architecture? Mealy, not melee. What do you think? Where's the output being derived from? It's melee. Yep, because it's being derived from combinational circuitry rather than directly from the registers. Good. So, in this particular one, we've got 2 registers, A and B, right? In this case, actually just flip-flops, not registers, because you need more than one for it to be a register. We have our X input and various combinational circuitry. So the inputs to the sequential components are determined by outputs from combinational circuits. Outputs of sequential elements that represent current states of those elements are fed back as inputs to the combinational circuitry. Yes. Y is the output. Inputs to the sequential elements can be described by input equations. So the input to the A flip-flop here can be described as A and X or B and X. In the case of B, it's just A naught X, right? Fairly straightforward. The output is given by A or B collected and X naught. The functional relationship among the inputs, outputs, and flip-flop states of the sequential circuit can be shown in the following state table. So you can see, separately labeled, including the input, we also have the present state of both registers A and B. In addition to the output, we have the next state of A and B specified, right? So we always have a deterministic path from the present state plus inputs to the next state plus outputs, right? The present state column shows the states of the flip-flops at any given time t. The input column gives the value of the input for each possible present state. Note that for each possible input combination, each of the present state is repeated. The next state column shows the states of the flip-flops one clock cycle later, right? As the next state of D flip-flop depends on the present input, values for the next state column must satisfy the equations given previously, right? Et cetera, et cetera. Good. So, going back to our circuitry, you can see these, first of all, that these little bits of the combinational circuitry are represented by the equations that we saw earlier, here, 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 and that, you know, the next states are being stored by them, etc., etc. So, the state table is a little bit cumbersome, and it takes a lot of paper, or screen space, I suppose, to represent something that could be represented in a more fine manner, or a smaller manner in more detail. So let's consider instead this circuit with the following state table, right? We've got two inputs, X and Y. We've got a flip-flop A, right? Essentially, we take the exclusive OR of these guys, take to that take the exclusive OR with the output of the flip-flop, and then run that back into the flip-flop, right? The output here is the output of the flip-flop. Is this Melee or Moore architecture? It's Moore, because it's being derived directly from the state element with no intervening combinational object. Good. If we were to represent this, as state diagrams, we would get the following, right? So, in depiction A, we see the states of the state diagram being the inputs X and Y, and the arrows being the outputs as well as the values stored in the register. In this case, we've got the value in the register and the output as the states, and the arrows are the other ones, the two inputs. Of the two of these, which is preferable? The one with fewer states, right? Yeah, this is much clearer to read, even though both represent the same thing. So, one thing that you might want, notice that because this is a Moore system, there can be no difference between the output given and the register, right? So really it's not even particularly interesting to include both in this one, right? It's like 0/0, 1/1. You might as well just say 0 and 1. They're the same thing, right? So, yeah. You guys have covered this stuff already, but yeah, good. So, state diagrams give us a pictorial view. Oh, question, yeah, sorry.
I was just a bit confused about how the circuit beforehand was for.
Well, the output Z is being picked off of the output of the flip-flop,
Oh, okay. Yeah.
right? Rather than being derived from any degree of combinational circuit.
Okay.
Make sense?
Yeah, I kind of forgot what Moore was for a second. I was thinking it was like the input, and I was getting confused.
Oh, no, that's, I think that you just got them flip-flopped, so to speak.
Alright, thank you.
Ah! Jokes. Ugh. Okay, thank you. I appreciate that. So, state diagrams give a pictorial view of state transitions and are more suitable for human interpretation of circuit behavior. State diagrams do not specify the time when the transition takes place. This can be done using a synchronous finite state machine using a clock input. So, most of the time, the behavior of the clock is assumed, so you don't put into your finite state machine diagram when the clock ticks X amount, when you receive a clock tick, then you do the transition. That's assumed. It's assumed that transitions will occur when the clock goes high, right? Good. Note the inputs and outputs in finite state machines are of Boolean data type. Yes. Good. And we can now talk about more complicated stuff. Any questions about that before we move on? Nope? Okay, good. So, single-purpose processors. We recall, I hope, the difference between single-purpose and general-purpose processors. What is the difference between a single-purpose and a general-purpose processor? What do you cut out when you turn something into a single-purpose processor? Yeah? Programmability, yes. So what we're going to do, what we do in order to produce a single-purpose processor is we take all of those components that don't need to be there, including the ability to reprogram the circuitry, we take those out because they cost us money, right? So what we do is we hardwire the program, right? So essentially what this is going to be is a set of slides on how one takes a program and implements it as hardware. All right? So, good. There's a couple of things that I'm just going to skip through because there's some overlap with the previous, I think. So, this is a diagram of the various modules contained in a digital camera chip. So, we have at its center a microcontroller, right? Excuse me. This is the general purpose computation center for general purpose tasks, right? So, as I stated over here, inside of the processor, we will have a portion of it dedicated to control and a portion of it dedicated to data path, right? So, in the case of a general purpose processor, a lot of the purpose of the control unit is fetching instructions from instruction memory, decoding those in terms of register operations and operations in the ALU, and then setting those various things to the correct value so that they can be executed. In addition to the general purpose processor, this digital camera chip also has what we might call a number of coprocessors, one of which is a JPEG codec, right? So, in order to encode JPEG images, that's one task, right? That doesn't require general purpose programming capability, right? All you have to do is produce JPEGs. And since it's a digital camera, presumably JPEG, you know, who stores JPEGs anymore? I know, but imagine it was like PNG or whatever the common format is these days. Whatever image format the kids are using these days. Since it's a camera, it'll need one of the, having one of those drastically accelerates the operability of the entire unit, since it doesn't have to run all of those instructions through a processor that has not been designed specifically for that task, right? One of the cool things that you can do with JPEG, or one of the coolest things you can do with single-purpose processors is you can take what could be a very long and complicated operation, and you can actually pipeline operations at the level of registers themselves, which is cool, you know? It's like, whereas, you know, this is kind of like particularly this applies particularly well to applications which we call embarrassingly parallel. Have you guys heard the term embarrassingly parallel before? So, in an image, right, each pixel has to be calculated, right? Each one of those pixels can be calculated reasonably independently. So, you can actually have a separate sort of processing core working on each one of those tasks in parallel, right? So, for example, right, let's say that you were working on a problem like rendering a video game, or rendering something inside of a video game environment. And I know this is kind of jumping into something that's not embedded systems, but I think it makes the point. So, inside of a video game environment, what is actually happening when you render a three-dimensional environment is you are sending rays out from the camera that's doing the in-game rendering, right? Each pixel gets a ray that goes out at a certain angle through the game environment. When it makes contact with an object in the game world, it then registers, you know, the color or whatever of that portion that it hits, right? If you want reflection, then you can reflect that ray off to something else, and then you can calculate like multiple rays all going into the same camera, right? Because each one of those pixels sends out its own ray, each one of those ray paths can be calculated by an independent process, right? In an ideal case, you would have one processor per pixel in your display, right? Now this is, you know, not possible because you know you would realistically probably only have like 1,000 cores in a GPU these days, and you know that would be like one scan line on your monitor approximately that you'd be able to process at once. And unfortunately, in the case of in the case of video game rendering, you only have to process it at you know 60 frames per second. So not 24 frames per second, 60 frames per second. So you know there are some you know there is some slack for not being able to process in parallel the entire thing, but you know this is essentially why you know pre-rendered trailers are the way they trick you into thinking the game's better than it is, because you know if it's pre-rendered, then they can just take all of the pixels over the entire thing, process it all up front, save those into a video file, and then show that to you, and then they can they can run much more complicated you know processes than normally they would be able to. But anyway, so the thing about single-purpose processors is they can be small and cheap and effective because they're only designed to do a single thing. We already talked about transistors. So there are perhaps. Okay, so this is one. So we already talked about multiplexers, right? This is like basic design, basic digital design components, right? We already talked about multiplexers. Who remembers what a multiplexer does? Yes.
It's like it has like a bunch of signals depending on the input. It outputs one of those signals.
Right. It's many to one. So, as I said previously, the thing that so if you imagine like inside of the ALU, right, you would have like an add function, right? It would have two inputs coming in, one input coming out, right? The thing that's sitting on top of the add function, right, is a multiplexer where all of the inputs to that multiplexer are all of the registers in your regular ARM register bank, right? All 16 of them, because you can select any one of those and feed it into the add function, right? The thing that does the selecting is the control unit, right? And of course you have one here, you have one for this one, and you have one for the output to see where the output gets eventually sent, right? That's how computers work. So multiplexer, very important. Decoders. You guys remember the, you remember in the digital to analog, the resistor string digital to analog, how we had like, you know, the incoming, you know, 8-bit number encoded as an integer, and it sent out, you know, 2 to the power of n controls to control signals to that many switches that select, right? That's what this decoder does. That's the operation of it. Adders, of course, just add numbers, you know, like summing like you would expect it. Comparison, comparators, you have two different signals. You can compare, see if one's greater than the other. Notice we get 3 lines out of that, right? Less, equal, that, or greater, right? So basically, you get one of the 3 of those depending on how the two numbers compare. Oh, and about adders. So the one thing to note about sum, right? A lot of these types of arithmetic blocks will have what's called a carry bit. The carry bit indicates whether or not the add operation overflowed its bounds, right? So if you have, you know, 1, 1, 1, 1, right? and you add 1, 0, 0, 0 to it, right, what you get is 0, 0, 0, 0, 1. But this 1 does not exist, like it's greater than the bound of the register that it's operating on, right? So this 1 gets dropped. It does not appear in the output, so that would not appear in the sum output. However, if this happens to happen, it gets sent to a separate carry signal, right? So you can still derive the information about whether or not overflow occurs, you know, sort of regardless as to whether you wanted it to or not, you know. So yeah, so that's overflow. Okay, get out of here.